I'm going to introduce Colin Paris, who is a Vice President for Software Research at GE Global Research, and is very involved in some really important things around industrial analytics, artificial intelligence, machine learning, and he's going to tell you a lot about that now. So, Colin, please come on stage. Thanks so much for being here.
My pleasure. Okay, good morning. Thank you very much for your time. It was a delight here to get the call from David and tell you a few things about what GE is doing. I'm going to tell you about GE's journey with two technologies. One is AI and one is additive manufacturing. We have these very long-lived assets, and I'm going to show you how we're actually using these technologies to make these assets more capable to adapt to the environments they're in. But first, let me step back and actually show you a little bit about the environment that we're in itself. Let me describe the landscape to you. So when you think about GE as being in three large industries: aviation, energy, and healthcare. When you think about aviation, we've got 70,000 engines, greater than 50% of the global fleet. So at any point in time, we have 300,000 souls in the air on these aircrafts. When you think about energy, 1/3 of the energy in the world is being produced by GE machines. When you think about human body scans, CT scans, MRIs, 400,000 scanners, 16,000 scans of a human body per minute. So that's the value to the society we're producing and to our customers. Now the drivers. The driver, number one, is always safety. Number two is always about productivity. How do I get more with these machines? Always, how do we find other ways to drive increased revenue for faster growth? And finally, how do you dynamically understand what's going on and react to it, reducing operational risk as well as reducing business risk? And there are a lot of dynamics, a lot of things are changing, and there are some of these below. I think you all know right now when we look at customers, we really are looking at end consumers. So we have to think about how does an end consumer have that journey on an aircraft? What do they want with energy? When we think of our markets, we have to think about two things. Where are our competitors coming from? Not traditional ones, but ones that can appear from nowhere. You look at Amazon and what's happening there. This is someone who does retail, now selling rockets to Boeing and Lockheed. You look at government influences. They're happening in droves when we have these discussions about what's happening with China and the US. And then finally, you look at the power of technology, the power I'm here to discuss with you. What is happening in AI? How do we use things that have occurred in the last 2 decades? We see the power of AI in consumers, where the data and the AI can allow you to predict the needs of a customer and then optimize a business model. Could I take that same idea as we have and predict the needs of an asset and then optimize the business model around that asset? That's the idea called a digital twin that I'm sure many of you know. We've talked about it for years. And that's the journey I'll take you on, using this AI and digital twin that forms the brain of a machine and trying to show how you could use that to change the body of a machine to ultimately form an immortal machine. So here's how this journey begins. It begins with what is a digital twin. So a digital twin itself is a model. It's a mathematical representation of an asset. Now, we all build models. The difference here, though, is that I am building a model that's constantly updating itself. It's updating itself every time the asset lands on the ground, it updates itself. It's learning not only from its experiences, the environment and how it was flown, but also the experiences of the fleet, of other models and other assets around it. And so what you do is you take the information, the physical information, the information about the design, the manufacturing, the services of this asset, and you combine it with the data. The data of every time it takes off, the environment it takes off in, the way it was used. When you bring those two things together using AI, it gives you the ability to deliver insights. An insight is something that says, based upon the way it's been flown, I can predict that this part will fail in 3 months. So I need to take an action. That's an insight. Or I can predict that right now fuel efficiency is falling, and in the next 20 flights, the fuel efficiency will be very low, and so you won't make as much money because you'll be paying for more fuel. Now, once I have the insights, that's not enough. I've got to take an insight and do an action in order to get value. So an action could be, I go get that part replaced, or I go and I wash that engine so I get out some of the contaminants so that the aerodynamics comes back and the fuel efficiency increases. So once I take these actions, I get feedback, and that feedback goes back into my mathematical model that gets it better. I learn. It's learning here constantly. It's learning from its environment, from the other people in the fleet. Then occasionally, because it's AI, I can actually look at a long-scale view of it, and I can learn things. Like we can learn things that say, normally we believe the biggest stress on engines were on takeoff, but in some conditions, when the engine climbs, there's an even greater stress. So now I can redesign better. So that digital twin is giving me a loop of learning at a faster rate than we can possibly learn as humans to allow us to have a brain that's better, allowing it to adapt and deliver greater value. And so what do we do with this value? With this value, we do three things. We try to figure out, how can I get early warning on a problem so that I can figure out a problem way before? So if there's wear and tear, I don't wait until the wear and tear is extreme. I can actually make a small change in maintenance, and I can get that asset back in place. That allows me to increase reliability. It allows me to do continuous prediction, because every time that asset lands, I can look and I can make a judgment on how long to keep it in service. Or I can make a judgment in something in which maybe contaminants are getting on the blades itself, and I should clean those blades, and that will allow it to fly even longer. It gives it increased availability. Or I can do optimization. I can look at a power plant and I can say, normally there's a lot of wear and tear if I increase the temperature inside the turbine to produce more electricity. Why don't I do this? Why don't I wait? And in cases where the cost of electricity is not high, maybe I actually run it inefficiently. And so I save that wear and tear on the parts. And when the cost of electricity is the highest, maybe when it's hottest or when it's coldest, or maybe when I don't have enough renewable energy, maybe then I increase the temperature and generate the maximum amount of electricity when the price is highest. I can actually increase profitability. So I can look at these three ways here, and I can increase reliability, I can increase availability, and I can increase profitability. And this we did. If you look at 2016 and 17, we created 1.2 million twins, and what we did was generate roughly $600 million in value. But this is an AI system, and we're dealing with trillions of dollars of assets, and so it's got to be first safe, not only operationally, but business-wise. So we've got to think of a way to use this AI effectively, such that this AI is used in the right conditions. So we created something called Humble AI. Now, what's Humble AI? Three distinct parts. The first part is the AI knows the zone of competency in which it is ideally suited to run. Usually that's based on where we selected, where we got the most data from. So it knows its region of competency. Then next is once it's outside that region of competency, we don't use the twin. We go back and we use a legacy-proven algorithm that has been there for years. And then the third thing is the twin says, help me learn to get better. Give me more data so that I could increase my region of competency. And that's the journey. So you look at this wind turbine. Here's what you find out. When you look at wind, wind is one of the most dynamic things on the planet. So that wind turbine, full length there is roughly 138 meters. And then you have the blades on top of it. What you find with wind is the wind that's going from 0 to 22 meters runs at a different speed than the wind that's in the middle of the turbine and the wind that's at the top. These are each running at different speeds. Then more than likely, what you also find is that different times of day, as you see on the graph, that speed changes. Then if you're on a wind farm and you have one wind turbine here and another one quarter of a mile away, the wind speed is totally different. And then you find in different seasons, the wind speed changes. And then you find with climate change, that changes as well. So to get a human being to write a mathematical equation to figure this out, impossible. Because based upon that speed, you determine how to pitch the angle of those blades, and you determine the speed by which it rotates to generate the maximum electricity. So you build a twin. You use the physics, and you combine it with the AI systems, with the data, and it finds you the right way of generating the maximum energy. But it does so where you have the best data. So for this, the region of competency is where you see that blue banner, between 6 and 7 meters per second, because I have the most data, and I've run all the validation tests. Now, when the wind speed increases during the day, during the season, outside of that region, we don't use the twin. What we do is we use a well-known algorithm. It doesn't give you the same performance, but it's known, it's safe, it's tested. And then what you do is you begin to collect data. I can collect data from that wind turbine. I can collect data from the fleet, the ones around it. I can collect data from a simulator that we're building with Sandia National Labs, or I can collect new ideas from humans. I have 4 ways of collecting data. And then based upon that, I get a larger region of competency. It now grows from 6 to 7 to 5 to 8 meters per second. Because of the new data, now I get a better twin. This is using this AI techniques in a lot safer way. I'm limiting the operational risk, I'm limiting the business risk. And we have deployed these on wind turbines. We are now deploying these on gas turbines as well. Humble AI. So now the brain of the system begins to get smarter. It adapts, and it knows where it's smart. It's not arrogant, it's humble. It also tells us things about the assets. It tells us things about the parts. The parts may break. So what do we do now? Can I use additive manufacturing to help me with those parts that break? Let me describe additive manufacturing to you a little bit. So normally what we do in manufacturing is subtractive manufacturing. Usually we take a metal, pour it in a mold, create an object, and then you actually take away the pieces you don't need, and then you polish the object. You may add certain coatings to it. That's how manufacturing is done. And it's done off a huge scale, because when I build a factory that builds these molds of the things, I am building hundreds of them. Now, additive is different. This is like 3D printing. What I'm doing there is I have a bed of powder, I put down a piece of powder, and I heat it with a laser. And then I add another bit of powder and another bit of powder, and I build a part up from the ground up. What it allows you to do is to build parts that are really different in design. So that small part you see there called a fuel nozzle. That's the part that sends the fuel inside the jet engines, and that fuel has to be sent in a particular way at the right temperature to cause it to ignite in the best possible way. That part consisted of 18 small parts that you have to bring together to get the right turns and twists so it doesn't clog. Those 18 parts become vulnerable all the time. Now with additive, you can build it as one part. When you do that, this is 5 times more durable. We've been building these for years. Then we decided, could we build an engine like that? All with additive parts. Now it went from 855 parts to 12 parts. The power of additive, and I can build one part custom-made for this one machine at a much lower cost. So now I actually take this brain that's telling me with the twin how to design things, giving me ideas of not only how to tweak the machine, but literally how to design a new part. And now I have that ability to take the twin, get data when I bring it in for inspection and improve the twin, get design data and through additive, and build a part that's perfectly suited. I have a brain and a body coming together. It's like me. I get smarter as I learn, and then I decide I have bones here that actually aren't functioning well, and I build a new bone that's stronger and quicker and more efficient. And as I do that, I create an immortal machine, one that's adapting to the environment constantly, understanding what the customer needs, delivering the value, both in terms of longevity and performance. Thank you very much for your time.
Right on time.
Any quick questions? Because I think I have something like 18 seconds here. Other than that, I will gladly give you the break. Questions, quick? Anyone? Please. Can't really see, but because of these lights, but somebody will see.
Great presentation. So
thank
you very much. What do you see as the big milestones? So over the course of the next 3, 5, 7 years, what do you think are the most important things to occur sequentially to get us to this point?
That's a great question. So let me give you the first one. The first one we had to go through quite a bit was to get past the cultural discussions with the chief engineers. So when you actually talk about AI and you go into a chief engineer who owns one of these assets and these things run $200-300 million, the first thing they say is, I don't believe you. I've studied physics all my life. This AI stuff is brand new. They aren't even textbooks. What do we do? So there's a series of toll gates. What they will do is they will actually not believe you at the start. They will pull the assets and verify the damage. And they will do this for months until they actually see, well, okay, you predicted it. This is what was delivered. And so that cycle goes on. So it's a cultural acceptance idea. That's the first thing that happens. The second thing that usually happens then is, okay, now that I've done that, how do I insert that into my business model? So usually there's a business process transformation that occurs at that point in time, in which many businesses say, well, if I can predict these things, how do I actually get it into my business process? Because usually it's a bunch of people sitting around deciding when to replace things. Now I have a machine telling it to you. So now I have to get that directly into the SAP systems that can generate new parts and get the right field engineer. That's the second piece you see. And then that's how they tie it to P&L. The third piece you see is how do you actually begin to train more and more people to understand these techniques? How do you build those twins fast enough? And so this is when you have to democratize enough AI and tie it with the physics to get it to be done. So it's still a journey as we move forward. And I haven't talked about additive as yet, because that is now getting there. But this is part of the journey that we see that we're on. But it is going to be cultural. It is going to be tied into a number of these things that related to the business models and everything else.